Protons, neutrons, electrons, oh my! Today we're going to be learning how to draw shell models to represent atoms and also how to calculate for the number of protons, neutrons, and electrons using some atom math. So hopefully by the end of this video you should be able to confidently draw a shell model for any of the elements up to number 20, and you should be able to calculate for protons, neutrons, and electrons. First and foremost, we need to do some review on what a mass number is on the periodic table, some general remembering from the past video. If you didn't watch it, please check it out. It'll help you understand where I'm getting these values from as well. Then we're going to jump into atom math. So we're going to jump right into calculating for mass, number of protons, number of electrons, number of neutrons, and then we're going to go into drawing shell models, also referred to as Bohr models, what they are, how we make them, and the Octet Rule. So first and foremost, the mass number quick review here is that if you look on the periodic table, we have this top value that's called the atomic number. That value is equivalent to the number of protons, and in a neutral atom is also equivalent to the number of electrons. The atomic mass, however, is the bottom number, usually the one that's got a bunch of decimal points after it. That's the one that is the protons plus the neutrons. Now remember, the protons are the ones with positive charge, the neutrons are the one with neutral charge, hence neutron. So those two together are inside the nucleus and they make up that mass value. The reason why these are typically big weird decimals is because neutrons are the reason for isotopes. And isotopes are naturally occurring different mass amounts of the same atom in nature. So what we find then is we take all of the naturally occurring variations and all of their different masses, because there's different amounts of neutrons, add them all up together, find the average, and voila, there you go. You've got your weird decimal point average of the mass of the neutrons with the protons for that atom on the periodic table. So if we were given a table like this, we should be able to fill it in using the information that we have learned. First and foremost, let's implore our periodic table regularly. So if you don't have one printed out, I highly recommend that you do. It's a lot easier to kind of go back and forth if you've got your chemistry soul right there with you, i.e. your periodic table, obviously. So if you don't have one, no fear, we'll kind of jump back and forth between this slide and the previous one so you can kind of see where I'm getting the values from. So before we jump into it, let's figure out what we need. For the first row, we're looking at chlorine. If you don't know the element symbol, then we need to go on a little bit of a hunt here, a little bit of a search. So looking through this periodic table, we're looking for the name chlorine. And hopefully you can see that pretty readily. It's above my head right there. So chlorine, number 17, is Cl. So let's go back to the previous slide, and we would write element symbol Cl for chlorine. We are given a mass number of 38. Let's look back at the periodic table. Does that say 38? No, it doesn't. That's okay, because chlorine can have isotopes that are naturally occurring with different masses due to a different number of neutrons. Now remember that the value that's here on the periodic table is an average of all the isotopes. In the table that I have given you, that mass number might be one specific isotope of chlorine that we're solving for. So that doesn't mean it's incorrect. We are still going to use the mass number of 38 that's given, not the value that's on the periodic table. We also have the atomic number being 17. That value is the one that's in the top corner up here. That's our 17 there. And that is going to be the same because chlorine will always be 17. If we were to add another proton and change it into 18, we wouldn't have chlorine anymore. We would now have argon, for example. So something completely different. Let's go back here. So then the number of protons is always going to be equal to the atomic number. Since it's already given as 17, my number of protons will also be 17. We're assuming that all of these atoms are neutral atoms. Therefore, the number of protons should be equal to the number of electrons in this case. So my electrons column for chlorine should also be 17. Now the question is, how do I figure out the number of neutrons? Remember that the number of neutrons is different for all of the different isotopes. In this case, we know we have an isotope of chlorine because the mass isn't 35 like it said on the periodic table. So we're going to have a different number of neutrons than the average from the periodic table. What we also know is that protons plus neutrons gives us the mass value. So we can use this as our kind of pseudo equation to solve for the neutrons, our n. We know that protons are 17. 17 plus n gives us mass, and the mass number we know to be 38. Set equal to 38. Now all we have to do is solve for n. What I do to one side of the equation, I have to do to the other. We have an equal sign here, so that's our little wall that we have to go back and forth across over. And I see on the left side of my equation that I am adding. So to undo addition, I need to subtract. I'm going to subtract 17 from both sides. And when I do that, n will equal 38. Get out your calculator if you don't have them already. 38 minus 17 is 21. So n equals 21. So I have 21 neutrons in this case. Let's move on to the next one. Germanium. Germanium, like for Germany, right? Jetzt schauen wir für Germanium. Wo ist Germanium? Wo ist es? Aha, Nummer 32 ist Germanium. Siehst du es? Vielleicht? No? Okay. The only reason I'm speaking in German is because germanium, obviously. Anyways, so we've got germanium as number 32, in case you did not understand my German there. That would be this guy right here. That's germanium. We see it's 32. We see its mass is 72.630. Let's go back to our table. Germanium's element symbol was Ge. G. The mass number we don't have yet, so let's make sure we fill in the other ones first in case it's an isotope. We don't just want to plug haphazardly what's on the periodic table in there. We want to follow what we are given in this table first. We know that the protons is equivalent to the atomic number, so the protons and atomic number should be the same always. Let's double check that. 32. 32. Awesome. So my atomic number will be 32 in the case of germanium. My protons and electrons will always be equal in the case of a neutral atom, so the electron should also be 32. Now the last thing I need is the mass number. Again, the mass is due to protons and neutrons together, so P plus N equals mass. In this case, my protons are 32 and my neutrons are 43. So if we add those two together, we should have our mass value. That should give us 75. If you don't like doing math in your head, again, feel free to use your calculator. No shame in it. I love using my calculator and I hate doing math in my head. So 75 would be the mass number for germanium. Let's move on to the next one. OS, like Oswald Cobblepot, for those of you that like Gotham on Netflix, right? I love that show. That show's awesome. Seriously though. All right, so we're looking for OS somewhere. So search the periodic table until you see OS as the symbol, and hopefully you are landing right on 76 there. That's osmium. Osmium, unfortunately not Oswald Cobblepot, osmium. And the mass number on the periodic table here is 190.23. But again, we don't care yet. We are going to check what the given value is first. So 76 OS osmium. Let's go back. Osmium is the name of the element itself, or the atom. We have a mass number of 190. Again, does that match? This one happens to match pretty close, minus the 0.23, but that's inconsequential. So if we go back, we need to figure out what the atomic number is. Do I need to look at the periodic table again, though? No, not really, because I'm given 76 electrons. And we know that in a neutral atom of osmium, the protons are always going to be equal to the number of electrons. Therefore, this would be 76. And we know that the atomic number is always the same number as the protons. So that would also be 76. Now the only thing we're solving for are these neutrons again right here. We're going to jump back to the equation above my head to solve for that. So we know the mass number in this case as 190, and we know the number of protons. So we know that our P plus N equals mass, and in this case, our proton number is 76. We're solving for our N, and our mass number is 190. In order to get N by itself, we need to undo addition by subtraction. We're going to subtract 76 from both sides, and we get N equals 2. Again, I don't like doing math in my head, so 190 minus 76 is 114 right there. Woohoo! And that's going to be the value that we can plug in for our neutrons. There are 114 neutrons in one atom of osmium. Last but not least, let's do tantalum. That's what Ta is. Let's find tantalum. Ta. Where are you, tantalum? Ollie, ollie, oxen free. You see it? It is number 73. That's tantalum. We also see that the mass is 180.95. Let's check back here. We've got Ta, tantalum. Is so tantalizing. So oh, by the way, what do you do with a dead chemist? You bury him. Unless you can cure him first. No? Okay. All right then. All right, so we've got tantalum, Ta, and we have a value of neutrons given, 113 neutrons. In this case, we need to go back and look at the periodic table for the atomic number in order to move any farther. So our number is 73. That's our atomic number. We're going to put that in right here. That number is the same as the number of protons, so that's going to be 73. And for a neutral atom of tantalum, the electrons are also going to be 73. And last but not least, to find our mass number, we have P plus N, proton plus neutron, equals mass. So my protons are 73, my neutrons are 113. If we add those two things together, we have 73 plus 113, and that is 186. So my mass number in this case is different than what the periodic table said. So we can't just haphazardly write down the mass from the periodic table, because the values given could be different if there's an isotope than what the periodic table average is. Please keep that in mind whenever you're doing atom math. Let's move on to shell models. So shell models are these really cool diagrams that we basically make to house electrons, or basically show how electrons live around a nucleus. Now again, remember, there is no orbit. There's no orbit. So just like Rutherford and Bohr found out, they thought that it was an orbit, a planetary orbit around the nucleus. This is not true. We have later found out that electrons are around the nucleus in more of a cloud or an electron density kind of format, in lobes, if you will, a probability of where to find them, not an exact trajected route. But we still use shell models because they're helpful to model some certain things. But just keep in mind that they are intrinsically false in that the electrons do not exist in specific orbits around the nucleus. So please remember that. What we do is we're going to write our symbol in the middle. If we're trying to model any of the elements from 1 to 20, we're going to draw a little nucleus. So a little circle. That's our nucleus, composed of protons and neutrons are in the nucleus. Let's say we wanted to model lithium. Why not? We'll go with lithium. I would write Li for the element symbol in the middle there for the nucleus. Then what I have are these things called shells, which are literally just circles around the nucleus. Like that. Ta-da! Shell model. Now all we have to do is put in the number of electrons. So in this case, lithium is atomic number 3. So 3 protons, right? So that's why I wrote the element symbol and the number of protons in the center, so you can kind of keep that in mind. So 3p, 3 protons for lithium in the center in the nucleus. We know that for a neutral atom, there has to be the same number of electrons as there are protons. So in this case, there would also be 3 electrons. This is where we start filling those shells with the electrons. And we fill them according to a certain amount. So in this first shell right here, we can only put 2 electrons, max of 2 forever and always. You can't put more than that in there. In the second shell over here, we can put a max of 8. And in the third shell, also a max of 8. So where it gets complicated is if you need to draw a shell model that's greater than 20 electrons, which we'll go over in a different video. Please click on that link either at the end of this video or down below in the description if you want help with drawing shell models that exceed 20 electrons. But for now, we're just going to stick with the basics. So in that first shell, we have 2 electrons. So we're going to play ring around the rosy. So 1, 2. So you can go like that, or you can go, 1, 2. Remember, electrons are negatively charged subatomic particles, so they're going to want to be as far apart from each other as possible. We note that we have 3 protons, therefore we need 3 electrons. We're still missing 1. So we need to now go on to the second shell. We're going to just plug in an electron. There. We have 3 electrons represented by these dots and 3 protons. So this would be a shell model of lithium, for example. Let's try getting a little bit more complicated here with a shell model of phosphorus. Phosphorus on the periodic table is right there. So if you don't have a periodic table out, again, I recommend you get one. Phosphorus is number 15, atomic number 15. So we're always going to start with our nucleus. We're going to draw a little circle. And in the nucleus are our protons. We have phosphorus P, and we have 15 protons. We have a certain number of neutrons. We haven't calculated that, but we could based off of what you just learned earlier. And we know that because there are 15 protons, there should also be 15 electrons that are balancing the charge. Remember, there's 15 pluses and 15 minuses, so they balance the charge together for a neutral atom. Now we need to fill in our shells and have a total of 15 dots or electrons in those shells. In the first shell, we can only fit 2. We're going to play ring around the rosy. So 1, 2, ring around the rosy. We're going all the way around. We still have 13 that we need to fill in. So we have to go to our second shell. In our second shell, we can fit 8. We're going to play ring around the rosy again. So we have 1, 2 already, 3, 4, 5, 6. Notice that I haven't been just haphazardly putting them together or in the corners over here or anything like that. I'm specifically spacing them far apart from each other because electrons have negative charge and they are repelling each other. We still have 4 more that can fit in this shell. What we're going to do now is pair them together. Notice I went around first and had lone pairs or lone electrons. They're all by themselves, right? They're all lonely, but now we can go back and pair them with a partner after we've played ring around the rosy. So we've gone around once, now we can go around again with an additional 4. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh boy. So now we filled up the second shell. We have 10 electrons, and we still need to put in 5. So we need to go to a third shell. Whew! That's a big atom. All right. So now we need to add an additional 5. Again, I am not going to do this. Okay, I'm even going to draw this in red. I am not going to go 1, 2, 3, 4, 5. I don't want to do that. Now, the reason you don't want to do that comes later when you're trying to figure out different charges, different ions, electrons gained or lost. But for now, just trust me. Please follow the ring around the rosy model and make sure that you go around first with lones and then go back and pair them together. So let's try that again. So moving on now to that third shell again. We need 5 additional, so 1, 2, 3, 4, 5. Notice how this model looks a lot different than the one I just drew in red, where there were 2 pairs here, 2 pairs there, and a lone at the bottom. This is a huge difference in the bonding and reactions that phosphorus can partake in. So please get used to drawing them individually and then going back and pairing them together as good practice, good chemistry bookkeeping and practice. So this would be your example of a complete shell model for phosphorus. So here are some directions. If you're more of a person that likes to have a step-by-step thing in your notes, feel free to kind of jot them down. The first thing that we do is always look at the periodic table to figure out how many protons and electrons there are for that particular atom, i.e. the atomic number is what we're looking at. Then we need to draw the nucleus, that first little circle that I put the number of protons in and also the element symbol, the chemical symbol. And then I draw the lowest shell that only fits 2 electrons around that. I add shells as necessary, playing ring around the rosy, meaning that I'm not pairing them up until I've gone all the way around once, at least. Then I need to move up to the next highest shell. So if I can't fit 10 in the first shell, which only fits 2, I need to go to the next shell and so on and so forth. Please remember that the order of filling is 2, 8, 8, and if you need to get up to that last 4th shell, which we haven't talked about, put a max of 2 in there for now until you've seen the more complicated way of making shell models. But keep it at 2, max of 20 electrons. Don't go past that for this method, please. Okay, so go ahead and give this one a try yourself. I implore you to pause the video at this time and give it a try before you see me make the oxygen Bohr model as well. Without further ado, let's begin. So, oxygen, we're going to first check our periodic table. And the periodic table says, hey, oxygen is number 8. Number 8, I know it's kind of hard to see, but it's number 8. So we have an atomic number of 8. We have an atomic number of 8, so that means we have 8 protons, and in a neutral atom of oxygen, that means we also have 8 electrons. So we're going to need to fill in 8. Let's start with our nucleus. That's our little circle. And we have an element symbol of O with 8p and a certain number of neutrons. We don't know. We don't care right now. You can calculate it though if you want to. We're going to now fill in 8 electrons. In the first shell, we can only fit 2. So 1, 2. In the next shell, we can fit a max of 8. So we already have 2, but we need to get up to 8 total. So 1, 2, 3, 4, 5, 6, 7, 8. Notice how I played ring around the rosy. I went all the way around first and then went back and paired up together. So I have 2 lonely electrons and 2 coupled electrons. Hopefully you got that same answer. Let's check out the noble gases. There's something very special about noble gases and their shell models, and we'll see why once we draw them out. Hopefully you'll be able to see the pattern here as well. All right, so for helium, helium on the periodic table is number 2, atomic number 2, which means there are 2 protons and 2 electrons in a neutral atom of helium. So we have helium, 2p, and we have one shell that fits 2 electrons. Alrighty, so 1, 2. Awesome. That's it. That one's done. Again, we're not sure about the number of neutrons, but you can calculate that if you look at the mass on the periodic table and subtract the protons from it. Okay, let's try neon. Neon is number 10 on the periodic table. So we know that it has 10 protons and 10 electrons. Drawing the nucleus, we have Ne, 10p, and in the first ring, we've got 2 that can fit there. So 1, 2. Now we need to move on to our second shell to fit the other 8. 1, 2, 3, 4, 5, 6, 7, 8. Interesting. Let's draw the last one first before we make any conclusions here. Argon. Argon is the next noble gas going down, and that is number 18. Meaning that it has 18 protons and 18 electrons. So argon we're going to put in the center here with 18p and a certain number of neutrons. That's our nucleus. In the first shell we can fit a max of 2 electrons. 1, 2. In the second shell we can fit a max of 8. Play ring around the rosy. 1, 2, 3, 4, 5, 6, 7, 8. Notice that even though I knew there was going to be 8 there, I didn't cheat myself and put 2 next to each other to shortcut it. Don't do that. Don't get in the habit of doing that. It's a bad habit and it'll trip you up. We need to keep going. We have 18 total, and so far we've only got 10 filled. So we still need an additional 8 in the third shell. Play ring around the rosy. Don't cheat it. Don't skip it. 1, 2, ring around the rosy, pockets full of posy, ashes, ashes. Such a dark song. Holy cow. Anyways, so now what you should see is that we have 18 total, and although the size is different between the different models here, what do you notice that's the same between them? What is something that is the same? Hopefully, you're picking up on the fact that the outer shell, the outermost shell, is completely filled. In helium, you can't fit any more in that first shell. 2 is the max. That's it. That's all it's got in its bank account. It's $2, right? Poor thing. And in neon, we see that the outer shell has 8. You can't fit any more than that. There's no lonely electrons there. They all have a date, right? And in argon, we also have the outer shell, the one that's all the way on the outside, also completely filled with 8. You can't fit any more in that shell. So what noble gases have in common is that they all have a filled outer shell. This is the Octet Rule. So the desire of every element to be like the noble gases. The noble gases are special in that they have that outer shell completely filled, just like what you saw. And what the other elements don't have is their outer shell completely filled. So literally, out of all of these elements on the periodic table, only these guys over here, the royalty, the noble gases, have that outer shell filled. That's special because it makes them stable. That ability to have a full outer shell makes them content in life. They are stable. Whereas the rest of these guys over here are all longing to be like the noble gases. They want their outer shell filled and they'll do anything to get it. And that's what gives us our chemical reactions and bonding to make molecules. So you should be able to now at this point calculate how many neutrons an isotope of nitrogen has if the mass number is 16. Calculate the mass number of manganese if it has 32 neutrons. And draw the shell or Bohr model for magnesium. Please test yourself. Make sure that you are able to do these 3 questions, and we will go over these questions in a following video, which I'll also link in the description below. Thanks. Hope this is helpful. Have a great ducking day.
When the thing went quack, 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 you man were ducking.